Our next session is also about 3D printer, specifically how to make 3D printer electronics. Please welcome Elias Bakken from Intelligent Agent.
Thank you. Hello, makers. How y'all doing today? Not too hungover, I hope? Great. Okay, 3D printer electronics. I've only got 20 minutes, so I'm going to talk fast. I've got about 17 slides. What you see on the picture here is a project that I've been working on for the last 2 years. It's a 3D printer electronics package. So you might wonder, okay, so what I'm going to go through is I'm going to show you some schematics. I'm going to show you some layouts. I'm going to show you some math. Yay! And a little bit of code. And I'm going to show you how this all sort of fits together. And using this, obviously, as an example, because that's the board that I know best. And I'm also going to share a few anecdotes or stories about stuff that I learned along the way. So hopefully you'll enjoy that. Okay. So why would we want to make 3D printer electronics? Or what are the things that needs to be optimized today? I would say that besides the actual workings of the electronics, that is stepping some stepper motors and keeping some temperatures, you might want to optimize towards low noise reduction, either EMC or audible noise. You might want a small footprint. You might want a low heat footprint. You might want a low price. A lot of people want that. Having connectors is one thing that you can optimize towards, so that you can easily disconnect and connect things. I mean, makers would like that. What else? Yeah, I think that sort of covers. Okay. Also, security, as in reverse polarization, safety features, etc. So there's still a lot to be desired, and there's maybe 10 or 15 electronics boards on the market today, and I'm sure there's room for more even. Okay, so I'm going to go through how the stepper motors are working. This is just an overview. So this board has 5 stepper motors. It has 6 end-stop inputs. Dual extrusion, and then, so I'm going to talk a little bit about how to actually set up a loop, proportional integral derivative controller, how that works, and then, yeah, okay, yeah. Okay, so starting with the thermistors. This is the schematic, as you can see. It's pretty basic. Across here you have a thermistor, and that varies varies resistance with temperature. So if you have a negative temperature coefficient, you have around 100 K across this at room temperature, and then you make a voltage divider, and so you can read out the voltage, and that changes depending on temperature, obviously. In my board, I also have a filter, a low-pass filter, to filter out some of the noise from the heaters, because they tend to be noisy if you do it right. Okay, so that's the starting point. Here's the math. So you have two equations. One is for reading out the voltage sensor, and one is a voltage divider. And if you combine those, then you can find the resistance of the thermistor, which is what you want. And then usually you have a lookup table. So you look up the resistor value, and then you find the temperature on that chart. And so this is not very linear, but with the voltage divider, this can be pushed into a different area. And so the largest derivative is around 100 degrees here. But this can also be shifted depending on where you want the highest resolution. Okay, so let's try to look at some code as well. This is code taken from Redeem, which is Replicate Daemon. So that's basically a program that runs in the background and interprets G-codes. So to get the temperature, what you do is you just read the ADC value from a file. You convert it to resistance, and then you use a lookup table to get the temperature out there. Easy, right? Okay, MOSFETs. That's also an important part of the electronics. This is the actual MOSFET that you see here. One of the things that I've added here is a amplifier. So if you look at a typical microcontroller, it has maybe 3.3 volts and a maximum of 20 milliamps of current. And if you're going to drive a MOSFET directly from that, then it's gonna use a lot of time to actually transition from on to off. And if you're having a pulse width modulation, if you're using that, then there's going to be a lot of heat generated, unless that transition is fast. So in the on position or the off position of the MOSFET, there's very little energy used in the MOSFET, but during the transition, there's energy generated. So you want that transition to go fast. So you might want to consider adding an amplifier, or a MOSFET driver, as it's called. Okay, so this thing, it's called a freewheeling diode. And the difference between not having one and having one can be seen in the oscilloscope pictures there. If you're driving a high inductive load, then it's going to put up a force field so that it might generate a very large negative voltage spike, and that might destroy your MOSFET. So adding a freewheeling diode that will eliminate that, and it will keep your MOSFETs from being destroyed, which is great. I've seen that happen to some of them, actually. So that's one technique to be used. Okay. So how can we control this? Here's some code. Pretty simple, right? Just set the power that you want, and then push that off via SPI, in this case. I'm using a pulse width modulation chip that's controlled via SPI, and it's that simple. I've eliminated a bit of the surrounding code so that it's simplified a little bit. Okay, so when you have both a thermistor and a MOSFET, then you can tie those together and try to keep the temperature, right? And so the preferred way in the industry to keep temperature is using a proportional integral derivative system or controller. So here's the formula for that. This is taken directly from Wikipedia. That's how I did it. It's basically just get the temperature from the thermistor, calculate the error, find the derivative, the integral, and then apply the formula, and then cap that off so you don't have more than full power. And then you set that power, and then you sleep for a second. Easy peasy. Okay, next slide fans. Fans are easy. Nothing special here, just an indicator LED, and these are what's called smart MOSFETs. So they have temperature control and also amplifier built into them. So it's nothing more to say about that. Okay, so the stepper motors. Here's a schematic for that. On this side, you have sort of these are the two coils that you have on the bipolar stepper motors. Voltage input and some current sensing resistors there as well. And then you have I would call it the interface. So there's the step and the direction pins. I'm sure you know that. And also you set the maximum current for each stepper motor, right? In this case, this is done with a digital to analog converter. And so we're going to look at how that is actually implemented. So stepping and setting the direction, that needs to happen fast. So these are connected directly to the microcontroller. But those other parameters there, like reset and sleep and enable, actually sleep and enable, I'm not sure why both those are there. And also micro-stepping. That's something that you don't need to do very often, right? It's typically something you do in the beginning as you boot up the board. And so that can happen in slow time, if you will. So in this case, I've used a serial to parallel converter and then hooked it up to an SPI port. So that that only happens one time. So it's doesn't need to use a lot of pins for that. Other than that, in the layout, make sure you place the decoupling capacitors close to the to the voltage inputs, and make sure you keep a lot of area for cooling, because they get hot. Otherwise, you need a fan on top there as well. Okay, so these resistors that I was talking about, they're quite large, but they're 0.1 ohms, so they're small in physical size, but or small in resistance, but large in physical size. And that is because the power goes right through them for the stepper motor, so they need to handle a little bit. So what happens in a stepper motor is that you apply a certain voltage across the coils, and then you watch the current rise until it hits that limit that you've set, right? And so you measure the current going through the resistor, and then when it hits that, you chop it off. And here is the formula for that, taken from the data sheet. And then we're going to look at how that is implemented in code. And it's pretty simple. So to set the current for each of the stepper motors, then you have the voltage reference that's set. You have the resistance, which was 0.1 ohms. And then you can calculate the voltage to set. And then place that into the, in my case, I'm using a digital to analog converter. So I'm calculating the DAC value and shipping that off via SPI. Okay. Additional circuitry. There's one thing that I'd like to talk a little bit about. This 5-volt step-down converter, I had a lot of difficulty with that. It gave me, it was way too noisy in one of the first tries. And so then a guy sends me an email, guy from Netherlands, I think it was. I never got his name, only his email, so I'm not sure who to credit, but he was at a hack space in Netherlands, and he's like, I saw your design online, and I see that you have a lot of bias. He was looking at this design. I see that you have a lot of bias, and if you just flip your stepper motor controllers, you're gonna reduce the number of bias from around 900 it is here to around 300, and that will do a lot of good things for the noise level on your board. So here is my take on it. That's what he said. And I was like, okay, well, I'm very conscious with my design. I don't think you've done I don't think you could have done such a good job that I've done. But then I opened his design and I saw this, and I was like, okay, wow, you've really done a good job. I mean, this is impressive. Okay, we're gonna go for that. So that's one of the good things about having an open design or having open source design. People will actually help you. And so looking at the results, this is what I was struggling with before. And so there was a huge noise spike every time the DC-DC buck converter was switching, and that happens a lot. So this is the 5 volts input. And what actually happened was that it was so noisy that the USB circuit had a under voltage lockout. So it went below 2.5 volts, and it sort of just shut off all the USB power. Using the guy from Netherlands hack, I was able to, I did a few changes as well, but the noise level was just reduced tremendously. So that's, pay attention to that. Do another loop on that. Or even consider having a 4-layer board. It's a little bit more expensive, but it might be worth it if you're struggling with EMC stuff. Okay, wow, I actually made it on time. Great. With time for questions even.
So are there any questions? Yep. Yep.
Are you in any 3D printers at the moment? Like, where are you at in your development at the moment?
Are you asking if this is implemented in any 3D printers in a large scale, or?
Yeah, or like, I mean, do you have users at the moment, and who's using it? And
Okay, yeah. I've sold around maybe 120 boards, and so there's around 80 customers, and a lot of interesting customers, it looks like, but I haven't got any large sales, if that's what you're asking. Yeah. So, okay, yeah, you have one? Yeah. Great.
Any other questions? Yep.
What are your considerations in terms of thermal managing temperature across the board? Did you do any simulations, or did you use a camera for that, or just?
Yeah, I wish I had the equipment for it. So the question was, what sort of thermal simulations did you do? I wish I had the equipment for it. I don't, but I've only felt the different components during high load, and it feels okay. Mm-hmm. So I've not had any components fail yet. Mm-hmm. And I've not done any modeling of heat
well,
either.
At least our experience is that if you add as much copper as you can, and also you'd order it with the thickest copper that is possible, that creates a better thermal distribution.
Yes, yes.
Yeah. Okay.
Good point.
Anyone else? No? Okay. Thank you, Elias.
Thank you.
Yep.